Welcome to the first Lean Workshop and to the first keynote. It's of course an honor to be able to do that. Before I start, I want to know who I'm talking to. So who of you consider yourself Lean users? Like already doing things with Lean, more or less serious? Okay, that's the big majority. Who of you are ITP users of other systems and you're here to be curious what the competition has to offer? Okay. Well, that would be a consequence. Okay, we have a hand raised from Chantal Keller. I don't know when she raised her hand, but okay, we got both crowds. But I assume all the people who've just raised the hand the second time are ITP users of some form, and I won't need to explain how to define the natural numbers in an theorem prover. Okay, just checking what the audience is. Okay, so this is called the report from the FRO. I say FRO, some people say FRO, it doesn't matter. And when I got invited to give this thing, I felt reminded of something that Simon Peyton-Jones does every year at the Haskell Implementers Workshop, or the Haskell Symposium. I actually don't know where it is. Where Simon Peyton-Jones, as the main developer of the GHG Haskell compiler, just gives a really broad and nice overview of what has happened in the community and in GHG in the last year. And he's doing a really amazing job of that. This is an inspiration. I'm not going to be able to live up to that. Also because I think what I should be talking about here is not just Lean the tool. I should be talking about Lean the community, about all the great things happening in MathLab, all the great things happening with all the startups using Lean. But for some reason, I'm not the right person because I just can't remember who did what. And I would be horribly confusing persons and places and events. So if Leo, for example, would be giving this talk, this would be much more on that. I decided, since I won't do a good job of that, I'll stick to what I know, which is Lean, the technical thing. And I hope this is still going to be interesting to you. But before I talk about Lean the tool, let's talk about Lean FRO, the Focused Research Organization, because not everybody may know what this is all about. The Lean FRO, this is one of our standard slides, it's a kind of a strange thing. It's somewhere in between a startup that's doing product development and like something you might find at a university. And these FROs as an organizational form is something that was invented by Convergent Research, a philanthropic funding foundation, to fill holes where you want to do something, but it's not something you can make money off, so you can't get venture capitalists to pay you. But it's also not quite something you might want to do as a research group because it doesn't produce papers that much, and you want something that has more attention than like one PhD span, where then the person leaves and you're left with the code. So this is a hole that in how we build things as a society that we're trying to fill here. And the Lean FRO was founded by Leonardo de Muro and Sebastian Ulrich, who were the main, well, who have been at that time the only and main developers, or no, I shouldn't say the only, but the main developers of Lean. And it was funded by multiple philanthropic organizations. So this is not research funding money. This is not investor money. This is really money where Leo and Sebastian went to some people who had a lot of money and told them this is great for society. And they said, okay, sounds good. Here you have some money. The problem with that money, I mean, I wouldn't say problem, it's great, but the problem with that money is that it's focused. And the focus of the Lean FRO is not to make Lean, like to just develop Lean for now, forever. The focus of the Lean FRO is to get Lean into a state where it's so useful and so good that it's not just used by enthusiastic mathematicians who we really love, but who don't have money, but also by commercial users for software verification, AI stuff, hardware verification, who then hopefully will find a way where they will notice that Lean is something that they need, and they will support the development of Lean in a sustainable long-term way. And the model that we're roughly aiming for here is what happens with Rust, with the Rust Foundation. And I'm saying this all not just to give you the background of Lean FRO, but also a bit to justify why, like what we build and what we don't build. And the point of the Lean FRO is to get Lean into that state. And that means making mathematicians happy is not always our first priority. And I see a painful smile on some parts of the audience. Not because we don't like the mathematicians or we don't think it's important. It's really important. Like the way mathematicians have used Lean is in a way a unique selling point for Lean. But it's not sufficient. So we need mathematicians to continue to use Lean, but like the little extra feature that is just fun to work on may not be the one that makes a difference in terms of will we have a sustainable Lean development ecosystem in 5 years. For that, we need to focus maybe on different things that I'm still missing in Lean for large-scale software verification, large-scale hardware verification. Okay, I said I don't want to talk much about what's happening in the ecosystem and things, but there's one thing I really want to. Oh, no, I'm still talking about the Lean FRO. What the Lean FRO really is of course the people in the Lean FRO, the employees, the team members that work here. This is a very nice picture, but maybe not very helpful. So I also have a boring picture. This was in Amsterdam during our retreat. We all distributed remotely, globally. And really globally, we have people in from your point of view, Northwest America, Australia, Brazil, which is great because the best time zone to meet is in Europe. So I don't have to get up early in the morning. I don't have to stay up late at night. Thanks for having people in Australia and West America. Okay. So this is our team. It's really large if you're considering, like, if you think of it as an open source project or an academic project, this is great. Which means we can do lots of things and we can maybe do things that we otherwise wouldn't be able to. The star means has joined since last year. I'm optimistic. I hope that this workshop and maybe also this slot in the workshop will be something that will happen regularly. So I just assume we had one last year, and everything I'm talking about is what happened in the last year. And I'll ignore everything before. Like we all have been here a year ago and got the last update. So star means joined since the last time I would have given this talk if we had started the sequence earlier, just to have some focus. Parentheses means these people have been at the FRO but have left. All for good reasons. People have this was like all planned. Yeah, sorry. Yeah.
So as you said, this is quite a big team. What's the goal of the size of the team of this organization? Is this the goal, or is the goal twice that size?
Oh,
as a person power, I mean.
I would say, I mean, I don't know if this is set in stone. I would personally expect currently we don't want to grow. This is already like from a point of engineers trying to manage engineers. We shouldn't be much more. When we are in this ideal world of a foundation, having funding in a foundation for this many people is probably even bolder than the idea of having funding at all. So maybe in the long run, some of these people will continue their academic careers. Some of these people may join the companies that are using Lean. So I wouldn't say if we have that much money, great, sure. I think we can also have a sustainable development of Lean in the long term that is with a smaller core team. But I mean, this is such an ambitious idea at all to fund software like this in that way that I can't make promises about how big the foundation will be.
Yeah, because I just counted and I came to somewhere between 2 and 3 millions per year just in salary.
Yeah,
and that's very impressive.
Yes. So this is true. We're in a way we're spoiled by funding. I shouldn't say spoiled. We really use the funding for good things. Please, dear funders, don't stop giving us money. But it is an unusual situation for a project like this. Oh, I forgot to mention, please ask questions anytime. I'm always more happy to answer questions you have than to just go through my program. And I will, I can be faster in the end if necessary. Yeah, and remind me to repeat questions because I always forget to repeat questions. Okay, these are the people, just so in case you want to see the faces to the names that you know from Zulip. And one of the reasons for, I mean, Joseph went for a PhD, that was planned. Johan, who's actually in the back in the room, is no longer a colleague of mine, and so is Anna, because of the next slide. One event that I want to include here is we got new funding this last year. Alex Gerko, a philanthropist, found that Lean is a useful thing to support and gave us some more money. And we actually have numbers here that you correctly calculated, like we're talking about millions here, which allowed us now to grow some more. And in particular, we have a dedicated team now with Jason Reed founding the team right now to focus even more on tooling and UX and things we wouldn't be doing otherwise. And there was also money going into a MathLab initiative. I don't know, are you talking about the MathLab initiative today? Okay. So maybe the summary, as far as I know, is, I mean, MathLab is a huge open source, lots of people meddling with the project, but there needs to be some, like at this size, you need to have some management, some infrastructure work, and this is now being funded. This is not taking over the control of MathLab in terms of deciding things like what goes in, what doesn't go in. It's supporting MathLab to run and to scale and to get even larger. All right, that was about the Lean FRO. Any questions about Lean FRO, about the organization, about the team, about how we do things before I talk about the Lean highlights of the last year? All right, Lean highlights. So when I like to give talks that are interesting. If I were to talk about the work we do proportionally to the amount of work that goes into it, it wouldn't be interesting. Because, and I try to make a picture of this, the thing we do, like there are really cool user visible features, but that's just the peak of the iceberg. And below the iceberg, there's performance improvements. I mean, very important to users, but not interesting to talk about. I mean, I could put up graphs, but yeah. There's stuff like internal refactorings or rewrites. The new compiler got turned on by default in last year, which means we got rid of a big chunk of technical debt that was causing bugs and didn't work and failed to compile and strange things. So big improvement, lots of work, but not much to say about then, hey, the new compiler is now on. There's release management, there's the interaction with MathLab, lots of bug fixes, of course, and then there's obviously this very little missing WHNF in your metacode that just breaks a tactic when somebody puts something behind a def. And this is just ongoing work, you know what I'm talking about. But not so interesting to talk about. So yeah, please.
Sorry for that, but I can imagine that this new compiler is for partially also written in Lean itself. Or,
right.
Okay, I was just
Lean, with small exceptions, including the trusted kernel, is all written in Lean these days. It's completely self-hosted. We'll actually see some Lean code a bit later, but yeah. All right, so with this in mind, let's look at all the cool user visible features, and just remember there's even more than it happened besides that. And I like to give my talks demos, which is always a bit tricky, but dangerous, but more interesting. So I'll start with tactics. We got a few interesting new tactics in the last year. The first one, chronology, yeah, okay. The good thing about doing live demos in the editor is I can fix my typos. and maybe I should even put in the underscore. Okay, that's better. It's a tactic that called BV Decide. It's about bit vectors. And it's one of these tactics that I like because they have a very clear goal, like clear domain of what they can solve, and they do it really well. So here's an example of a highly non-trivial proof. So we have two specifications of pop count, number of bits set in a uint32. The first one is basically the loop. You count up the bits. That's easy. And then there's, maybe you've heard about the book Hacker's Delight. It's a book full of really strange tricks to do things with bits. In particular, they claim that this code here is calculating the pop count of a 32-bit number by doing shifts and other bit operations. Now, if you don't believe that, you can use Lean. So we write the two functions. We unfold the definition. In particular, this simp call here will unfold the recursive loop here. So we basically have unrolled the loop into 32 calculations of bits. Not very efficient. At the bottom, if you scroll down in the goal, we see that here's the right-hand side, also a bit unfolded like this. The code here has sharing. Here we don't have that sharing anymore. You don't want to prove that manually, right? You don't have to. There's no BB decide, and I mean, that's maybe the downside of these nice automatic tactics. There's not much to show. It just solves the goal. So how does this work? This is a really elaborate setup where the tactic takes the goal, it simplifies a few things, it tries to identify everything related to bit vectors, so fixed width numbers, bit vectors themselves, Boolean operations, of course, and then does some of the things a SAT solver does. If you know about BitBlast and AIGs, then maybe that. In the end, you get the standard form. You pass out, or the tactic passes to a SAT solver, an external SAT solver, because these things are highly tuned machines. We didn't want to re-implement a SAT solver. But we don't trust these highly tuned machines. So what we get back from SAT solver is a certificate in a format called LRED. And then Lean, we have a verified checker that's proven in Lean to be correct. That's checking the LRED proof, and that's what you then include in your proof. So very powerful if you do anything with bits, software verification, maybe hardware stuff. Also, maybe little for those who want to see how Lean uses, how it's to use Lean like. We have features like this. We can ask BB decide. So maybe the SAT solver runs a long time. You don't want to run that every time. So you can say BB decide question mark in a tactic always is, or often is a variant that allows you to replace a tactic with something faster. In this case, if I say BB decide question mark, it'll actually write out the result from the SAT solver to a file, and it'll suggest I can actually replace this proof by another tactic that just uses that certificate directly, and now the proof runs faster. As long as I don't change anything. Okay, this is a binary file. I won't need to I don't think I should show it. Yeah, okay. The question is whether the file is too long to include. The file is 4 megabytes of binary data. I don't know if that answers your question, but I'll leave it up to you.
So the translation to a SAT problem is also proven? So it's also trustworthy?
No, okay. So what's verified is the bit blasting and the transformation. Yeah, so the transformation all the way to the conjunctive normal form is verified.
Okay.
And then the certificate is used to prove whether this is unset.
And then you check that there is some. Okay, yeah. Very good. Thank
you. Yeah. So no external trust anymore. Yeah. Yeah. Okay. All right. So this is a nice tactic for. Yeah. Okay. Yeah. Somebody must have pointed out in a room with Matlab people. So the verified checker here. This is a Lean code that is verified within Lean, but it's run as a compiled artifact. So when you're using BB decide, you're actually trusting not just the Lean kernel, but also Lean as like the Lean compiler and toolchain. This is still, we argue, a much higher level of assurance than just trusting a SAT solver that is not verified. It's not the high level of assurance you get when you only allow things that run through the very small Lean kernel, as Mathlib, for example, does. So Mathlib doesn't allow this tactic. The next tactic doesn't have that problem. Okay, so this tactic is really great for solving a specific goal. Another big tactic that we got last year, and this is really a game changer, I think, is grind. So if you may know that Leo de Muro was also the author of Z3, SMT solver, and SMT solvers are great at solving Like you give them a theory of like your functions, your equations, and they just say, oh yeah, I can solve it. This is, and they're really good at that. They're not so good when then the proof doesn't go through and you need to figure out how to make it go through, which was motivation, or one motivation to actually start the development on Lean. But they're still really good at proving certain things. So it's only reasonable to have something of that kind integrated into your interactive theorem proving. And this is what Leo has created with the grind tactic. So the sorry. The core idea is the grind tactic looks at the context of your goal or the assumptions. Here, for example, we have a little example. We have some, maybe I should go here. We have some predicate that is reflexive, and we know that the function g is involutive, maybe, and somehow really g relates b to a, and then it can prove that goal. And I think the mental model you should have for working with a tactic like this is it takes all these equations and put them on a whiteboard, and then it tries to derive new equations from it. I guess that's a congruence closure as an idea. Now, just blindly, what?
Blindly is probably not the best.
Right. So blindly is not a good idea. The first problem you would face if you do it naively is that it quickly explodes because you have many, like if you have a term with two arguments and you do some rewriting here, or have multiple choices here and multiple choices there, then you get a combinatoric explosion. So the representation is very smart. It's using equivalence classes even inside of the terms. So this is the one key idea. And then it's clever, or it's trying to be clever in when it instantiates a theorem with which values. So there are patterns that activate certain theorems. But from a user point of view, I think the important thing to know is that it's not as directed as a rewriting term system. It's not like sim where you have to carefully construct all the things you pass to sim so that the left-hand side goes to the right-hand side. Grind can take equations and work them both ways. And this is probably also happening here. We can peek a little bit in what grind is doing if we remove H3 from the context, because then grind fails because it's not provable. And we can get some diagnostics here in the info view. And this is also, I guess, if the idea, this is not just for debuggers, people debugging grind itself. This is really meant for users to, if they really think this should be solvable by grind, and then you can learn to read these diagnostics. In particular, there's the equivalence classes. So grind has figured out that A is equal to g of A, so it has instantiated this universal quantifier with A, and something about g of A also to g of A. For some reason, it stopped there. It doesn't create longer ones. It's very promising. So even though it's a black box SMT solver in a way, you get some insights. And this may be a crucial feature for in practice, because one of the complaints of people using theorem provers that build on Z3 or on SMT solvers is that if the proof fails, it's really hard to know how to make progress. So we're taking this into account, and there may even be soon an interactive mode where you tell grind more exactly what to do step by step. Okay, so if grind was just congruence closure and e-matching and e-graphs, that wouldn't be, oh, maybe first this. And then of course, just like the simp, it's really important that if you're working with some existing theory in MathLib or in Lean itself, that grind just knows the important theorems about things there. And yes, you can annotate things. So for example, here's a theorem. F of this long expression should be yay. But if I ask grind to solve it, it says I can't solve it. But we can tell grind to use a theorem, and then it can solve it. And yes, the sum of the cubes from 1 to 9 is indeed 2025. I couldn't do this next year. And then one thing as a library author you would do is you don't want the users to have to specify the theorems there. You would start to carefully annotate the right theorems in your library with the grind attribute or one of the many variations of the grind attribute. I will not go into that, but you can read it in the manual, like basically telling grind when to use that theorem, when to instantiate it. And then the goal is that there are many user-defined theories where you just, as a user, you just use grind and it just often solves all the trivial things. Yes, please.
But if you were to give the definition of F, then it should work also, wouldn't it?
Let's try. The question was, well, I guess you heard it. I can also give the definition of F, yeah, which is more or less equivalent to giving the equation of F to grind.
Okay, so what you just presented is a trick that is more used when it's way too explosive. So the theorem F 2025 could be some intermediate step, which itself was very costly to prove.
Yes, costly or just not a trivial consequence of your definition. Like if your definition is the real numbers are the Cauchy sequences, then you can't expect grind to from that derive interesting facts about the reals. And then you develop your API. We talk about APIs as if theorem proving was programming for some reason. And if it's carefully designed and well annotated, then lots of theorems will just be proven, independent of the precise definition. Okay, so this is already cool. What makes it even more cool is that grind has this whiteboard where it puts these equations, but it doesn't just try to solve them alone. There's a whole set of satellite solvers that also look at this and see if they can make sense of this with domain-specific knowledge. And there are a few that are built in. Linear integer arithmetic, so this makes grind subsume omega. Linear arithmetic over fields and rings, commutative rings, AC solver. So grind can solve lots of goals that involve computation in an ever-growing. I mean, I can't keep up with how quickly Leo adds new solvers and makes these more powerful to grind. So I will probably not go into detail here, but rather let you look at the documentation by the time you're back, because maybe here did another one.
It says you can write your own. Is that true?
Yes, it's true. This is actually relatively new, not yet in the latest release, but Leo has now made an API interface to grind that you can instantiate and write your own grind solvers. A bit like Simprox, if you know what that means. So yes, you can, if you have a nice decision procedure and you can easily recognize when to use it, you can throw it in. And this is better than just having a tactic which does something and then another tactic solves it, because your solver can add new facts to the whiteboard. It can derive new things, and then some other piece of grind or some other solver continues working with it.
We have a question online, is what happens with inductive predicates and functions?
With inductive predicates and functions. So grind does case splitting. It's not very good at, I mean, it can case split. It's not meant for goals that need heavy case splitting. So if you have an inductive data type with many constructors and you want grind to blast through all the options, then you're not using the right tool here, but it's possible. It doesn't do induction, for example, if that's the question. But we'll get to that on the next slide. Great. So grind is great, but it's not doing everything. For example, it's usually not the right tool if you first have to figure out how to do induction. Now, often induction is trivial, like you have some AST and you do induction on the AST. But sometimes you have a function that is, oh yeah, one question more over there.
There is the green only. Is there also a green question mark to obtain the green only as with SIMP?
It's coming.
Okay.
It's definitely planned. Yeah. So one of the new ideas that I heard from Leo is that there will be an interactive mode in grind where you tell him more like in smaller steps what it's doing. And then grind question mark will take the result of the search and turn it into this interactive thing. And then you have better insight in what's doing. It's going to be faster and maybe even useful for interactive proofs where you want to prove, where you want to be involved in this conversation with the whiteboard as a user. Okay. Any last question about grind? All right. So the other thing that I'd like to point out, because it really fits well with grind, is what's called fun induction. This is something I built. I've been using Isabelle in the time before Lean, so half of the things I'm building for Lean is just building the things that I really liked about Isabelle, and I want to have in Lean. So what's the problem? The problem is if you have a function definition, like the Ackermann function, that is not just structurally recursive. and you want to prove something about it, you will find and you will learn, or maybe somebody taught you, that almost always the proof should follow the structure of the function. Same recursive structure, same case splitting. In Lean, that's okay. You can just write a theorem that is recursive. This is something that is mind-boggling to people from HL, but because it's dependent type language, proofs are just definitions, they can be recursive. And if the termination checker is happy, that's basically you're inventing your own induction theorem, induction principle on the fly. You can also use induction if you set it up the right way. But it's just tedious work every time. You have to repeat the recursive structure of the function, and then you have to do the case matching in the same way. And if you do the unfolding as in the function. So this is all packaged up now in a tactic. It's called fun induction, no pun intended. Oh, did I not disable hovers? It's really important to disable hovers during a talk, because otherwise it's yeah, okay, that's better. So here we have a goal about the Ackermann function. It's larger than the sum of the arguments. And if I use fun induction on the function call, it'll give me 3 goals corresponding exactly to corresponding exactly to the 3 cases of the function, with the goal instantiated, with the function unfolded, and this is maybe the most important bit, induction hypotheses exactly only for the recursive calls of my function, not just for all NM that are smaller lexicographically. And this really fits well with automation tactics. Oh, I didn't undo my practice because originally this was just story. Oh well, let's just pretend I started here. Because now you get these simple goals, and you can use simp for this one, and you can't use simp for this one, but of course I need to use induction hypotheses, so maybe I'll use simp star. So this works. Let's try this again. Okay, it doesn't quite work, but we just learned about this cool tactic that does rewriting in multiple ways. So let's try grind. Yes, grind works. Perfect. And this is, for me, this is the goal for interactive theorem proof. You have your definition, you set up your induction because that's the clever part, and then the rest is automation. Can I use grind for all of them? Good question. Let's try. I can use it for this one. I can use it for this one. Okay, not surprising. I guess I could even now use like small syntax for use grind on all goals. And another nice feature of fun induction is if there's only one call to the function in the goal, then it's very likely I want to use these arguments, so I don't have to specify the arguments. And this is now so small, like this is silly to even write. Like surely the system can come up with that. And this is the other thing I want to show off. It's try question mark. It's already useful. It will become more useful next year, I think. This is a tactic that tries a few common things, including combinations of induction. Like it finds there's a function call there. Let's try fun induction, and then try simp and grind on the goals. And it tries to find the best of the goals, the best of the tactics itself. And you can even, nice feature for those who are not using Lean, you can click on these, and it just gets replaced in the goal in the editor. And maybe in the future, this try question mark will just run automatically. And then you're in a world where you just write your theorem, and it pops up and telling you, I know how to do that. And you just say, OK, I'll take your proof. Yes, please, question.
This might be a naive question. I just know Isabel. Is there a way to have variables be arbitrary, like you have in Isabel, if you want to free your induction hypothesis with fun induction?
With induction and a fun induction, you just write generalizing.
Okay.
Cool. That also is inspired by Isabel, I think. Can you pass the mic? Yeah, so this works. All right, this was fun induction. I think the last tactic I want to present is something. Oh, maybe before I talk about the tactic, this is interesting for the non-Lean users here. I said I'm coming from a background with Isabel. That's only partly true. I'm also coming back from a background of Haskell. So I'm really fond of pure functional programming and of monads to capture this. It just feels the right way. It's just sometimes very tedious. And Lean has do notation, just like Haskell, but Lean added a few more features. That has been in Lean for a long time now, to make do notation a bit more useful. In particular, if you have a do notation, a function in do notation, you can use mutable variables, and you can use early return, and then putting quotes around them, because this is just sugar, just syntactic sugar for pure functional programs under the hood. But it's just so convenient if you just have a small function and you want to break out of a loop, or you don't want to think about how to map M or fold it, to just briefly write a for loop and you know it's still pure. This is not imperative programming. This just looks like it. And this has been really useful for programming with Lean. And you can use the identity monad to, in pure function, quickly go into that mode. So this is a style I use a lot when I'm programming in Lean. But at least until a while ago, or until recently, verifying functions like this was just very tedious. It was possible, but you had all these, like whatever this desugars to in the way. It was really hard to get to the core of the proof. So we now have a tactic for that. It's called MVCgen for monadic verification condition generator. And I can now prove this function to be correct. There's a little bit of dancing I have to do to get in the right shape, and then I use the tactic. And of course, if you know something about imperative verification, it's all about finding the loop invariance or specifying the loop invariance, because once for every loop you have the invariant, the rest is often just automatic. And this is also the idea here. You have the tactic, you specify the invariant. The invariant is a bit complicated because we have a loop with early return. If I didn't have the early return, we could have something simpler here. But I have to state the invariant that if I'm returning, then there are duplicates in the function, and if I'm continuing, then the prefix of the things I'm iterating through is free of duplicates. Let's not go into too much detail here. And then at the end, I get a bunch of goals. We get 5 goals, probably corresponding to all the steps in the proof. And I don't even want to look at the goals. They're a bit ugly and large. But luckily, we have grind. And again, things fall into place. And this is a reasonable way of doing verification of like boring imperative programs. You specify the loop invariance, and the rest is automation. OK. 20 more minutes. Let's see. This is another thing I stole from Isabel. And I kind of like it. Because, yes, Lean is this type theory thing, and everybody cares about termination and things. But sometimes you just want to write a function and want to verify it, that you either don't know whether it's terminating, or you don't want to prove a priori that it's terminating, or maybe it isn't even terminating. But you can, and you still want to be able to do that. And you can do that now, at least for a certain class of functions, using a feature called partial fixed point. It's opt-in, because the partial is, you kind of want to see that something is partial here going on. But for example, yeah, this is the F91 function, a benchmark for termination checking. I can avoid termination checking. So I don't have to worry about whether this is hard for termination checking. Another example might be finding the smallest element, the smallest natural number larger than x that satisfies a predicate. This is also obviously a non-terminating function. But maybe I still want to write it as code, and then I still want to prove some things about it. This is all sound, and so this uses domain theory under the hood. Again, Isabel users will recognize that maybe from function partial. And yeah, you can still prove things about it using generated partial correctness theorems.
Question. So
yes.
Does the nat, like, can you run nat.find? Like, does it run similar to the partial?
Yeah, from the point of view of the compiler, this is just like partial. So I can use, GitHub is suggesting some very nice example. If I don't know if I should try running it on false now, because it may crash the server and I might have to restart, and I don't want to do that. Yeah, but basically, this is a fundamental thing about Lean is the compiler, the one that goes to compiled code, always sees your function as recursive functions, and it doesn't care the least about whether it's marked as partial, whether it's structurally recursive, whether it's well-founded recursive, whether it's partial fixed point. It's just a different branch. This only matters when you go towards the kernel for verification. OK, I will not dwell too much on this. Also, a nice feature that you may sometimes need during software verification is co-inductive predicates. I'm saying predicates, we don't have conductive data, different beast. But for predicates, things are easier, and we can define them easily without changing the core logic of Lean. And right now right now you have the ability to define them by an equation. So the conductive predicate that asserts that an element is the start of an infinite sequence in a relation. You can give that by basically by saying, well, it isn't in that predicate if there exists another value that it relates to, and that is the starting point of an infinite sequence. And then you get a conduction principle, and you can prove things about it. And soon you will also be able to write this in the familiar syntax. So you will have just write conductive like you would write inductive, and you can define conductive predicates that way. You were about to ask a question, or? Oh, it looked like you were. Okay, never mind. Looked like, never mind. Okay. Okay. Another feature related to definitions. So maybe you've tried to define rose trees before. These are trees where every node has a list of subtrees. So we have nested induction. And if you have nested induction, you want nested recursion. And a year ago, this was tedious to, tricky to write. You want to write a map function that is that the recursive call is hidden behind a higher order function. And this is not a partial fixed point. We want to prove termination. But if you don't know what map is doing, you don't know whether that map is really calling this function only on elements of the list. So it's kind of unclear whether this will be a nicely terminating function. And you had to go through hoops with like the attach function, if you may remember. We've now added a mechanism to Lean that essentially uses a simpset to do these transformations for you automatically, but hides it from you mostly. And which means this now works, and it's extensible. So let's say I want to recurse through a tree, just to make it a bit more meta here. So I can't just. So what I would be doing is, and this kind of explains the idea behind it. I define a copy of the map function, in this case, the map on trees, that calls the function f that you pass to it on an element of the tree, and it passes also a proof to that function, type theory benefits, that the element is smaller than the tree that map was called on. And this is precisely what you need to make termination go through in a well-founded recursive manner. And then you notice that these are actually the same if you don't use the proof. And you can, okay, let's maybe, so this is the function definition we want to do. We want to recurse through a tree map. I'm actually recursing twice because why not? So we have a tree of trees in the tree. And this doesn't get accepted. And we can see the problem here. The termination checker complains, I can't prove that this element is smaller than the parameter because they're completely unrelated. I don't know how they relate. But if I now send this lemma, register this lemma in the right way, that the termination checker should replace the tree map with our tree map prime that has the termination proof hint in the context of the recursive function of its argument, then the proof just goes through. Okay, so suddenly questions are up. Well, just go in sequence, I don't know.
So, excuse me, so your tree map X, the one you're using is then recursively replacing the F in one way or another by another one. The extra parameter which you were saying that the size must be larger, then it's going to change that one in the recursion. Anyway, I will have a look at it.
Okay, so the point is, for termination checking, I'm looking at the context, the local context of f. Maybe I should write it like this. And it'll extend the local context with a relation between x and ts, and this will be picked up by the termination checker. Was there more questions? Yes.
Did you present the map prime function to us for educational purpose, or does one have to provide it? Because it seems like it could be automatically generated.
Could be. Not sure if it's worth it, because this is off. I mean, if you know about the problem, it's not too hard to write it. If you don't know about it, then I don't know how often you write recursive function and recurse through it. I mean, maybe yeah. Maybe there could be more automation. The first step is to make it work, and then the next step might be to automate it.
Okay.
Not sure if that would be worth it at the moment.
Comment and question. Comment, the nested inductive thing in the experience in ROC is whenever the developers say, oh, this doesn't happen very often, and also it's easy to solve, in the end you get the same question once a week on ROC Club. And it's like literally about this.
Right.
But real question, does this generate efficient code?
The code generated, this is basically the point I made earlier, looks at that definition.
Okay.
So everything around this is just convincing the kernel that it exists, and you can specify things about it. The kernel always runs on the, basically takes the equations, not the definition to compile.
Meaning this
the compiler takes the equation, not the definition.
But that means this new technique extends the TCB because you need to trust that match.
We're deriving this equation. Like this is
okay.
So
okay, yeah.
If you look at tree map, tree map, wait.
Okay, yeah. It's the whole approach kind of. If you have equations, you can use the equations for code extraction.
Exactly.
Yeah. Okay. Cool.
Oh, did I change something here? Yeah. Okay. Doesn't matter. We should. Oh, I'm slower than expected. Okay. Let's. I've showed you new tactics. I've showed you new ways of using definitions. How do you manage this complexity as a user? How do you work with the tool? So let's look at usability, because this is also something that we care about a lot, and maybe, yeah, and we've been improving things a lot. So as a user, you really benefit from incrementality and parallelism. Incrementality means that I have a proof. These sleep 1000 just means a tactic that runs very slow, 1 second each, and I can edit this subproof, and the proof above doesn't get reevaluated. And you can imagine this needs to be carefully constructed, and once you have it as a user, you just take it for granted because it's so important for your daily driving. Parallelism goes a bit further. So so we can see on the left what's being processed. If I edit the whole file and reload the whole file, we'll see that this proof here is still being processed, but I can already work on the thing below. And this works because in almost all cases, you don't care about the precise theorem of precise proof of that theorem. You can still use the theorem down there. This wasn't the case a year ago, and I've seen people. Oh, this is a fun anecdote. I've watched some Lean users who had like a 3-page long, 3-screen long proof, and they were adding a letter and was reprocessed the whole proof. We still had parallelism on the command level, but basically the whole proof would go through. And they would wait for half a second. And I was asking them, like, how can you work with this? And they said, oh, this is great. This gives me time to think. It's amazing what users accept and rationalize. And I'm thinking, like, how? Okay, so I'm glad that this is no longer the case. Okay, oh, this is maybe my favorite section of this talk. So we invest a lot into the interactive usability of Lean. With like the language server and the VS Code plugin, and here a quick overview about like some of the big things that have happened in the last year. In lay hints, so in Lean you can omit binding A, and it's just being implicit. But doing something implicit silently is really dangerous. You make a typo, and suddenly something in your proof is completely strange, and you don't know what's happening. So to the point that MathLib has disabled that feature because it just was so confusing. Now what happens if you don't write the bind of A is that the editor will show you that something was implicitly bound. And I need to quickly enable hovers again. just to demonstrate this. You can hover on it, and it. Oh, did I disable them? Sorry. Hover enabled. Oh, modified it in workspace. Yes. Okay. You can hover on it and see the type, and you can even just double click on it to make it explicit. So I think this is a game changer for like just make a useful feature suddenly usable, because useful and usable may not be the same thing. All right. Got the decorations. If you have a proof that's not complete, there are now a few things that tell you what to do. There's on the left, you see the error range, and you see where the error starts. This is the incomplete block, but you know how far it goes down, because this is where you have to continue. The symbol indicates where you should be working on next. And this improves understanding goals much better, because previously, if you well, I'll skip that. This is something that's maybe hard to discover, so I really want to point out that it exists now. If you have an unknown identifier, you can right-click on, you can hover it, or you can press Control dot, and it'll suggest the right imports. Yes, advanced users don't know this. You have a quick fix that will find that there's a hash map in a library, in a module that you haven't imported. It'll suggest importing the library and even changing the identifier to be quantified and to be properly in the, like now we have this import up here. Okay, I'll disable the hovers again. Okay, signature help. I'll go quick demo mode now. If you write a function, I need to have space. It'll give you the current type of the thing you're defining. So you know the parameter names, you know what parameters are missing. You can now start instantiating parameters in the wrong order. And it'll give you the instantiated remaining type. So it's much more easier to work with these things when you don't know the precise. Precise type. Stop. Okay. I'll skip that one. And go to definition. You've had go to definition for a long while. If I press Control click on net, you go to net. That's easy. What happens if you Control click on plus? It'll give you all the things that contribute to this definition. You'll find the type class that has the operation you're just looking at, but it'll also show you the instances of your concrete thing you clicked on. In particular, you will find the concrete instance for additional natural numbers. And then there's more. Okay. I will skip this. I will skip that. There are lots of things in the standard library. Sorry, standard library people, that I have to be shorter now. But you can read about that there. The module system is a big one that's coming, or that's implemented. And basically, without going through the demo, there's no difference between things for the public, like for consumers of your module that just import you, and things that they shouldn't see. And this is great for information hiding. This is great for having a nice API. What it's also really great for is compilation reavoidance. And I want to demo this because this is really important. So this is in the Lean source code, somewhere in the SIMP code. Lean is written in Lean, yes. One feature that we added is module hierarchy. So I can click on this module and see all the modules that use this one. This is a module that is being used all over the place in many things. But still, if I change a function in this module, and this is a non-exposed function, and I save, I want to cheat, and I go back and build this, it will, it's slower because Zoom is running. This always happens during talks, right? The demo is really fast, and then, so it's rebuilding this module. It's rebuilding 4 other modules, which I don't know personally why, but now it's building Lean and it's done. Now, if you've been using Mathlib and you've been changing a proof somewhere and you wanted to build a module further down, didn't it always feel silly? Like you're changing a proof. It doesn't matter downstream what's happening. Once Mathlib has adopted the module system, you will get this experience there as well. Okay, Lake Cache will save you a local disk drive when you have multiple versions of the mathlib in different projects. We have a reference manual. It's highly interactive. It's automatically checked. So things come up to date. You can hover, you can click, and it's built on a library that you can use yourself to implement interesting artifacts like references, blocks, things like that. Okay, at end of demo time, we have a new homepage. It's much more pretty. It's no longer embarrassing. It's the second attempt. The first one was shut down by the community with bad feedback, and we listened to that. And we now have one that's written by engineers who also happen to have an aesthetic sense, unlike me. But this is now a much nicer homepage, so it feels much more mature. This is just a list of the things I just showed you. I will skip the roadmap because it's online. But there are great things coming up, so looking forward for the next talk here in a year, when we can maybe hopefully discuss all of these things and more. And with that, we have maybe a minute or two for more questions. Thank you.